Like Jenny said, we're going to be talking about water today, and I got a bottle of water here because it's kind of hot out. Where it comes from, why it's important, and what we do with it if it's not good enough to drink or something like that. So, start this off, let's go ahead and talk about where the water came from. It basically came from the beginning of time. When the Big Bang started, if you ever heard of the Big Bang, that's basically where there's this big explosion, all matter, all time, all space came from a single point. And what was made then, basically when things cooled off, was hydrogen. So we've got a cloud, I mean basically the whole of interstellar space is made out of hydrogen. And so when that gathered together using gravity, gravity is a force that basically makes all masses come together. Then it heated up so that we had a reaction where 4 hydrogens basically reacted using the heat that's involved, and we're talking millions of degrees, plus the pressure that you can imagine that orders of magnitude, like 10 to the 30th hydrogen atoms basically, would be compressed together, and it formed helium. Now that was the first thing that when a star starts that happens. But then when the star runs out of helium in its core, it'll basically stop producing this energy. I forgot to tell you, there's also gamma rays that are produced by that. And that produces the energy that stops the star from contracting. But then when that energy's gone, it'll start to contract again because the gamma rays aren't produced. And you have a situation where 3 of the heliums, when it gets hot enough again, will form carbon. And we've also got a reaction where they form oxygen. So that's where the oxygen comes from in the formula H2O, which I think most of you know that that's water. And that's basically where the water came from. And we didn't have oxygen until hundreds of million years after the Big Bang started, which was about 15 million years ago or so. Once that formed, of course, a lot of that oxygen went throughout our universe. It got in other clouds that had hydrogen in them, clouds that had helium in them. They also had carbon and oxygen. They also had a lot of other iron that's produced, everything that you can think of, aluminum, neon, all of these things are produced by explosion of stars, the very massive stars when they die. And what happens is that in what's called the solar nebula, a lot of this water, a lot of these other elements ended up being there, and it ended up formed our solar system. And of course there was a lot of water that was in the cloud, so it got tied up in the minerals and things that made up the Earth. There were also comets. You guys have heard of comets. They're basically big chunks of ice that circle the sun. Halley's Comet is an object that circles the sun in about 75 years. And that gives us, I mean, it basically comes near the sun, it melts, and that rains down on the Earth. It basically got attracted by gravity to the Earth's surface. And that's where a lot of our water came from. But it also came from volcanoes. When there were volcanoes that outgassed, there was a lot of water that was produced in that case as well. All right, so that's the story of where water came from, basically. Now, why is it important to us? Well, it's said that life started in the water. And I don't want to get into exactly what happened. This isn't a show on evolution or anything. But there's a lot of life. We chose this park, Citizens Park, in order to use the lake back there as a backdrop. And there's a lot of life. If you take some water from there, which we actually did, there's a lot of water and life that exists back there. You could see, maybe I should bring it up closer so you guys can see it a little bit more. There's a lot of sediment in there. That's probably algae and other sorts of plants. But life is in the water. Life needs water. We need to drink water. That's why we've got these bottles here that we're going to drink, and I better get a drink, stay hydrated. But this water is important because most of our body is water. You know, we excrete water as we live. We also need to replace that water and make it part of our bodies as we go through the day. Sorry, the gnats are getting me. But I think that what I would like to say is that when we get water from a lake like this, it's got all that stuff in it that we looked at there, and it basically is not something that's suitable to drink a lot of times. We do things like have farms where there's a lot of fertilizer and things like that that go into the water. You've got other pollution. We drive these cars that give off a lot of nasty chemicals, and they float through the air, and eventually they get into our water. And you know, people go and they throw things in the water and pollute it that way. How do we go about separating this water and making it something that we can actually ingest? So there's a lot of nasty stuff that ends up being in the water, and we've got to somehow purify it and make it better. Now, one way of doing that is doing what's called electrolysis, where you would actually apply energy to the water, to the H2O, and what you do in that case is you form H's and O's. Just to make sure it's balanced, I think I need to do 2 of those. But anyway, if you put an electric current on the water, you have 2 electrodes basically that you do that with, you'll produce hydrogen and electricity, and oxygen. And that, when you combine that again, it just takes those 2 elements and you make pure water again. That's one way that you can do that. Travis Bates, give you his intro. He is an instructor of chemistry. Like I said, he's the co-sponsor of the Science Club. He has his Bachelor of Science from the University of Oklahoma in biochemistry. He earned his Master's at Florida State University in chemistry, and he's been teaching here at Chipola for 4 years. I'd just like to turn it over to him, and he will go ahead and tell you about another way of separating water out and purifying it.
Thank you, Dr. Bodart. So he did an amazing job, so thank you. Okay, so I have the honor today to talk about the chemistry of water, and I'm going to talk about a few different parts of it. But in a second, we're going to do a distillation where we're actually going to try to separate all of the gunk and everything in the water, and the goal is to only get pure water to come out over here in this test tube, in this Falcon tube. But before we get to water, I kind of want to talk about some of the properties of water and what they have. So right here I have water in a cup. It's literally just a cup of water. But what's awesome about it is that it's just a bunch of large water molecules here, and they have little magnets built into them to kind of show us how water flows. So water has this amazing property where it sticks to other water molecules. And you may notice this like in raindrops, that raindrops have this kind of circular oblong shape as they fall from the sky, and they like to stick together. Same thing with lakes and everything, that the water all wants to be a part of one group. And that's a really important attribute for life because it makes water kind of concentrated around. So what makes this special is on our water molecule, we have the oxygen in the center. Unfortunately, oxygen, the chemical symbol for that is O, and atoms are also round like an O. Not the best thought out process. But then they have 2 hydrogens, and the hydrogens are much smaller than the oxygen atoms. As Dr. Bodart was talking about, hydrogen is the most common element in the universe. It is the smallest atom, while oxygen's a little bit more rare. It's only made from the fusion of hydrogen inside stars. Oxygen's a lot rarer in the universe. So on one water molecule, we have, in this case here it's red, visualized, we have in the center, and then we have 2 hydrogens coming off the sides. Oxygen has this ability to pull electrons towards it, and it doesn't share the electrons evenly with the hydrogens. So what happens is this oxygen, by pulling electrons towards the center of the nuclei here, gets a small negative charge on it. And then the hydrogens on the outside get a slight positive charge on them. So through some fancy physics things with Coulomb's law, these opposite charges end up causing things to stick together, just kind of like magnets. So if we have two water molecules here, the positive charge on the hydrogen and the negative charge on the oxygen actually causes them to get stabilization, and there's an attraction between them, and they want to stick together. Since water is a liquid, at least under regular conditions out here today, they're able to flow around each other. These connections that are between them are really, really weak, and they only last on the nano time scale that they break apart and the new one is formed between the other ones. So in a real glass of water or a beaker of water, there's going to be lots of these different water molecules all flowing around, rearranging how they're put together. Because water has this negative and positive ends on it, it's also really good at dissolving things that have charges on them. So if we think about salt, salt is one of the most common things that you need to survive. Salt just has small sodium ions and chloride ions that have charges on them. And when these charges interact, depending on if it's a positive or negative charge, it's going to cause these other water molecules to stick to them. And this is what makes water really good at dissolving stuff. Our cells are filled with water, and then we also have proteins, sugars, DNA, nuclei, all this other stuff inside there, and they're all dissolved and have water molecules flowing around them. These positive negative charges kind of correspond to how they match up. The difficulty is, though, is because these things are attracted to each other in this nice blob, is that when we go to separate them, we have to do something to pull the water molecules off, but get rid of the charges. So Dr. Bodart already talked about in the beginning about using electrolysis, that we can use electricity that selectively breaks things apart. What we're going to do today is we're going to use distillation. So in distillation, what we're going to do is we're going to use our nice little propane torch here, and we're actually going to selectively boil this lovely mixture. There's even some things floating in here. There's like a lot of nice gunk in there. And the goal is the water is going to boil off while everything else gets left behind. So we're going to do proper safety protocols here, and Jenny, the Science Club president, she's going to help me do some of this right here. So we're going to be wearing goggles and gloves to be safe. So we have a sample of water that came from the lake behind us, and we got lots of nice lovely gunk in this here. So what we're going to do is we're going to pour a small amount here in this round bottom flask. Do you want to pour some? I think that's probably about good. We're just going to do a small distillation. Okay, and we've got all sorts of lovely stuff in here. Luckily our water's pretty clear. That looks good, but there are some leaves and other debris. So we're going to seal the top. And the goal is, what we're going to do is whenever we apply heat down here, it's going to vaporize the water. It's going to go from the liquid phase to the gas phase, or the vapor phase. It's going to climb up here, and then hopefully it's going to make its way down in here. Normally this is called a condenser jacket. We'd be running cold water through here to condense the water vapor back to the liquid phase. Unfortunately, we don't have running water out here and it's not really worth it, but we're gonna have it condensed down in here and then it's gonna drip into our lovely Falcon tube at the end. So let's see if this will light on camera. All right, hopefully this works well. All right, so we're gonna start by slowly heating the glassware. So Jenny, I'm gonna hold this for a little bit and then I'm gonna get tired and then you're gonna hold it for a little bit.
It's like going on the same.
Okay, yeah. I'm a little scared that we're gonna heat the glassware a little too fast, but I think it'll be okay. All right, so now we're just gonna wait for this to boil. How long could that take out in the heat? Okay, more fun facts about water as we're sitting here and waiting for this here. So when we talk about acid-base chemistry, water has the ability to both be an acid or a base depending on the reaction taking place. In that operation there, so water is really good about dissolving different substances, and it's also able to act as an acid base, means that it goes through a wide range of reactions. If we think about like photosynthesis, the process of converting sunlight into stored chemical energy, plants require a tremendous amount of water for that process. It's something like 6 water molecules for every sun photon they need to convert that over. So what's happening is these water molecules are being transformed into a higher energy format, and that's what's able to store the energy there. So Jenny's doing a really good job in our distillation. So you can kind of see now the water's starting to bubble there. I can see the water vapor starting to rise up in our glass column. So it's kind of getting towards the top there in the cork. So now our goal is we need the water vapor to start coming this way, and then it's going to cool back down to the liquid phase, and hopefully we get some nice drops that are going to come into our falcon tube. Okay, it is really boiling now. So any 5 minutes from now, we're gonna have some drops of water. So distillation is a very high energy system to clean water. It works really well because it separates everything that's not water out, but it actually requires us to boil the water. The water treatment plant here in Mariana and local municipalities, they actually clean and purify the water through filters, through osmosis, through using biological systems, that they're able to use chemicals where they don't have to boil the water. Instead, they're just taking care of the different things dissolved in there, and they're actually selectively dissolving things back in there to give the water a good taste and a good pH and a good minerality on it. Okay. I already said this 3 times now, but the water is definitely really boiling at this point. Yeah, I see it all. Oh, okay, I see the water vapor's reached here. Yeah, unfortunately, I think without the condenser, it's not condensing back down. We'll see what happens. I see there's water forming there. Okay. Guys, this is very exciting. We have very small droplets of water forming right there. How fantastic. All right, I think we're gonna call this here. I think we've demonstrated what's happening. All right, so since we don't have cold water running through the condenser here, it's kind of got water vapor that's hot all the way throughout there, but we actually are getting some water condensing down here and in the falcon tube. It's just in very small amounts. I think we're proving here that on distillation here that it takes a lot of energy to boil that water out, but only pure water should be moving this way here. All of the salts, all the life, everything else is gonna stay inside the round bottom flask. Only the water vapor that's going into that phase is able to climb up out of there and leave. Okay, that's all I have for the chemistry of water. We have completed our stuff here.